2027, two vehicles will determine the future of the global automotive industry. One of them has no steering wheel. The other needs to cost less than any electric car ever sold at mass scale. What connects the two is a machine that no traditional manufacturer can replicate, and one that is redefining what it means to build a car. For decades, building a car meant the same thing: stamping dozens of steel parts, welding them together with hundreds of robots, assembling everything on kilometre-long production lines. It was an expensive, slow process, riddled with failure points. That model worked for over a century. Now it is being destroyed, not by a new business strategy, but by a machine. The 50,000-ton GigaPress is not a larger version of what already existed. It is a complete rupture. To grasp the scale of what that means, the most advanced die-casting machines available today operate at 16,000 tons. The new generation arrives with triple that clamping force, the equivalent of 500,000 tons of pressure applied to molten aluminium at approximately 850 degrees Celsius. At that temperature, the material must fill extremely large and complex molds before solidifying. Older machines inject around 80 kilograms of aluminium per cycle and frequently encounter premature solidification. The 50,000-ton GigaPress eliminates that risk, with speed and force that simply did not exist before. But the number that truly changes everything is not the force, it is the productivity. A conventional die-casting machine produces a single structural component per cycle. The 50,000-ton GigaPress can produce up to 5 massive parts simultaneously, with each cycle lasting between 1 and 2 minutes. That means thousands of large components can be manufactured daily, without increasing operational complexity. The physical floor space required in the factory drops dramatically. The labour required plummets, and the entire process becomes radically simpler. To understand why this is devastating for the competition, consider what the manufacturer was doing before. A single structural component was formed from 70 to 100 stamped steel parts, joined by hundreds of welding robots. Now, all of that is replaced by a single cast piece. The reduction in factory floor space reaches 40%. Labour costs plummet. The supply chain shrinks. This is not an improvement on the old system, it is the elimination of it. The precision involved is equally impressive. The molten aluminium is purified to remove impurities larger than 25 micrometers, smaller than the thickness of a human hair. Immediately after injection, the part undergoes a controlled thermal shock, cooling rapidly from around 400 degrees Celsius to 50 degrees, which locks superior properties into the material. Speed is fundamental, but consistency is absolute. This combination of scale, speed, and precision creates a cost advantage that completely transforms the equation for the affordable electric vehicle. A single 50,000-ton GigaPress costs between $43 and $65 million, with additional tooling between 1.5 and 2.5 million. It is an enormous investment. But by eliminating hundreds of parts, dispensing with large fleets of welding robots, and radically simplifying the supply chain, the return per vehicle produced changes entirely. It is this mechanism that makes the target of an electric car below $25,000 possible, something that, with traditional methods, would be mathematically unviable. Historically, there are two moments that transformed car manufacturing irreversibly: Henry Ford's assembly line and Toyota's lean production system. Both increased efficiency within an existing model. What is happening now is different. It is not about doing the same process with less waste, it is about eliminating the entire process and replacing it with a completely different one. And the rest of the industry knows it. In 2027, manufacturers from the United States, Germany, and across Europe are under extreme pressure to adapt. In Europe, the response has been cautious. Some manufacturers are adopting smaller 9,000-ton systems, combined with modular design, to avoid catastrophic production risks. German manufacturers, historically proud of their precision engineering, are growing increasingly uneasy in the face of large-scale castings advance. In the United States and Asia, billions are being invested in new casting facilities to avoid being left out of the market before 2027. Toyota is being forced to rebuild its electric vehicle manufacturing base from scratch, with the aim of eliminating up to half of its production steps. Nissan is pursuing the consolidation of around 100 separate components into a single cast piece, with significant cost and weight reduction targets. These are real moves, but there is a fundamental problem with this race. Whilst traditional manufacturers treat large-scale casting as a solution for surviving beyond 2027, it was built as the foundation of an entire manufacturing philosophy. The difference is not marginal. It expands exponentially as scale increases. Every effort to close the gap, whether through European engineering discipline or American capital, risks arriving too late to a transformation that is already underway. Two specific vehicles are the only ones that can fully exploit the potential of a 50,000-ton GigaPress: the Cybercab and the Model 2. The reason is simple. This scale of manufacturing is not an incremental upgrade. It requires the vehicle to be designed from the outset around the logic of casting. Legacy models cannot adapt without compromising efficiency, cost, or structural integrity. The Cybercab represents the most extreme case. Designed for autonomous operation without a steering wheel or pedals, it is free from the constraints of traditional vehicle architecture. As a robotic taxi operating 24 hours a day, 7 days a week in a fleet environment, it must withstand far more intensive usage cycles than a privately owned car. That demands a highly rigid structure with the fewest possible failure points. By casting the majority of the body as a single massive unit, hundreds of joints, weld points, and vulnerable interfaces are eliminated. Fewer parts mean fewer mechanical failure points, lower maintenance requirements, and faster repair cycles. To produce the Cybercab at a scale of millions of units annually, necessary to make a global autonomous taxi network viable, this level of structural simplification is not optional. It is the only path. The Model 2 faces a different but equally critical challenge: price. With a target below $25,000, it competes directly with low-cost manufacturers that dominate the most fiercely contested stem of the global market. At that price point, traditional methods simply do not deliver acceptable margins. Every part, every stage of the process, every second of production time must be eliminated or compressed to the maximum. Industry estimates indicate that the combination of the 50,000-ton GigaPress with the modular production process can reduce manufacturing costs by up to 50% compared with conventional assembly lines. The factory floor space required falls by around 40%, labour requirements drop by approximately 25%, and the total production time is compressed dramatically. The Model 2 is not merely a cheaper car, it is a vehicle designed to be manufactured by a system that removes thousands of components and eliminates kilometres of assembly line. This battle does not take place in a vacuum. In the low-cost electric vehicle segment, Asian manufacturers already dominate, with strategies based on maximum supply chain localization, cheaper labour, and modular architectures optimized for cost reduction. Models such as the Wuling Hongguang Mini show just how far it is possible to go by compressing margins and simplifying assembly. But that model has clear limits in terms of durability, scalability, and long-term efficiency. The strategy being built around the GigaPress moves in the opposite direction. Rather than optimizing a fragmented process, the objective is to eliminate fragmentation entirely. Whilst one approach struggles for efficiency within the existing system, the other rewrites the entire system. For the cybercab, the competition is not against other cars. It is against cost per kilometre. In a world where autonomous taxis operate continuously, what matters is not the purchase price, it is the operational cost over the vehicle's lifetime. A vehicle that is cheaper to manufacture, more durable, and easier to maintain translates directly into a lower cost per kilometre than any alternative involving a human driver. That puts pressure not only on manufacturers, but also on ride-hailing platforms and urban mobility systems. What is taking shape is a war on two fronts. On one side, cost minimization through scale and labour efficiency. On the other, technological disruption and radical manufacturing simplification. In 2027, the winner will not simply be whoever builds the cheapest car, but whoever redefines how cars are built from the very first step. The Cybercab and the Model 2 share a common mandate: to be produced at extreme scale with a radically lower cost per unit. One optimizes for fleet utilization and durability, the other optimizes for affordability and mass adoption. The 50,000-ton GigaPress is the only technology capable of sustaining both objectives simultaneously. That is why these two vehicles are not merely new products, they are manufacturing platforms. By building them around large-scale casting from the very first component, the automobile is being redefined, not just in design, but in the way it is forged, scaled, and distributed globally. If you want to follow how this transformation unfolds over the coming years, subscribe to the channel and give it a like. It helps the content reach more people who want to understand what is truly changing in the industry.